Hello, in this video I'm going to solve question 6, problem set to lecture 3, lectures in elementary number theory. Determine all integer solutions of the equation x cubed plus x all over x plus 3 equals 35. Pause the video at this point and give it a try. Okay, now we solve the problem here. So I'm looking for all integers for which this fraction on the left becomes equal to 35. Okay, I want to use the theorem that I presented on lecture 3 in the same playlist, elementary number theory playlist. Okay, so I'm not claiming by no means that this is the only way to solve the problem, but I try to use the theorems that I presented during the lectures so that you become more comfortable by using them. Okay, so I would say that if this is going to be the case, from here I can conclude that x to the power of 3 plus x equals to 35 x plus 3. Okay, so from here I can conclude this one. And then from here what I can conclude is that 35, which is an integer, is multiplied by this number and it is equal to this number. So this means that x plus 3 should divide x to the power of 3 plus x. If you are following my videos on this playlist, you know that if I want to solve these kind of problems and find all values for x, all integer values for x, it would be better if I have a constant number on the right. If I have a constant number on the right, and then x plus 3 is easy to find, because I would say that x plus 3 will be an integer will be an integer factor of the number on the right, and the number on the right has finitely many factors, so then by equating them I can find x. Okay, so my goal is to make this a constant. One way to make it a constant, you can do it gradually. So one thing that comes to mind is to get rid of x to the power of 3 first, or if possible, simultaneously both of them. And from here, I want to use a theorem that I mentioned on lecture number 3. If I have a divisibility relation, a divides b, a and b are integers, if I want to, and if I know that this is true, if I want to, I can add any integer multiple of the left-hand side to the right-hand side. I will get a new divisibility relation, but the theorem asserts that if this one is true, the new one is also true. So it means that I can keep the left-hand side, I can write b, and I can add an integer multiple, m is an integer here, of the left-hand side to the right-hand side. So if this divisibility relation is true, and if m is an integer, this new divisibility relation is also guaranteed to be true. And we also showed in lecture 3 that this theorem is reversible. In other words, if you have a divisibility relation so that an integer multiple of the left-hand side appears as a summand on the right-hand side, that integer multiple can be dropped. If this is true, what is left after dropping that term is still true. Okay, so here, what I want to do, I want to use this theorem in this direction. There is this algebra that I am doing is by no means unique, so you can find your own way. But to expand your perspective, to broaden your perspective, let me do it in this way. I will keep x plus 3 on the left. I will keep x to the power of 3 plus x on the right. So I want to give the role of a to this, and I want to give the role of b to x cubed plus x. And I will write it as a minus x to the power of 2 minus 3x plus 9 times x plus 3. First of all, I want you to understand this is indeed true, yes? If you compare this one with the right-hand side here, as I told you, a is x plus 3, b is x cubed plus x, a is again x plus 3, but for m, I have chosen this combination. Okay, because if x is supposed to be an integer, this combination is also definitely an integer. But what is the benefit of that? I intentionally did that because I have an algebraic identity in mind. If I expand that, this becomes the first one cubed plus the second one cubed, which is 27. And now it becomes clear why I did what I did, because this x cubed here and minus x cubed are gone, and then I am left with x minus 27. So this becomes a simpler one. So it becomes x plus 3 divides x minus 27. I will consider this a progress because I started with a divisibility relation. The right side was a third-degree polynomial, but now I have a divisibility relation. The right side is a first-degree polynomial. By the way, all these arrows up to here are reversible. Why? Because instead of x minus 27, I can write it in this form. So this one is reversible. And then, because this theorem was reversible, I can drop this multiple of the left-hand side. So this means that this arrow is also reversible. And if this arrow, if we have this one, be careful, this one is not reversible. Because there is no guarantee that the constant number should be 35. So you see, unfortunately, this step is not reversible. So it means that if I start simplifying what I am doing, and I solve that last simplified version, that last simplified version is not guaranteed to solve my original problem, because one of these arrows will be not, as you will see, is not reversible, and this is this arrow. Okay, but now you see that I haven't reached the goal yet, because I want to have a constant here. So I have to get rid of this x. But getting rid of this x is very simple now, yes? What I do, I will now give the rule of a to x plus 3 again, but this time I give the rule of b to x minus 27, and I give the rule of m to minus 1. Okay, so this becomes x minus 27 minus 1 times x plus 3. Okay? And by the way, this is also reversible because this theorem is reversible. And then you see that minus x that comes from here will cancel that one, and it becomes minus 3, minus 27 is minus 30. So this means that I can continue and conclude that x plus 3 divides minus 30. And this one is also reversible because minus 30 can be written here. So you see that from here to here, they are equivalent because all the arrows are reversible. So it means that if I find any solution for this, that is guaranteed to be a solution for this. But unfortunately, this is not what I want, because I want to grant this one. And this one will not conclude, I cannot go from here to here because that arrow is not reversible. So that becomes a little bit boring because I have to find all possible values, and unfortunately there are 16 possibilities there. Okay, so for example here, I can say that x plus 3 should be an integer factor of minus 30. So how many numbers are there? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, and finally plus or minus 30. 1, 2, 3, 4, 5, 6, 7, 8, 16 possibilities. Okay, and that is the reason I said that it is unfortunate that this arrow is not reversible. If this arrow was also reversible, then I am okay, because I will find x from all these 16 equations, and all of them will be acceptable. But all of them will be acceptable for this one, but not necessarily this one. So I have to do 16 trials and errors, okay? And I have already done that myself at home before starting the video. So I realized that only x equals to 7 is acceptable, which comes from the fact that x plus 3 is equal to positive 10. The only one that will give me the correct answer is this one. So if you take 7 with you and put it here and do the calculations, you really you will see that it becomes 350. But none of the other ones will work like that. Okay. You might say that, okay, this is too lengthy, I can do it a little bit faster. For example, if I started from here but multiply this there, let us see what happens. So this becomes x to the power of 3 plus x. I multiply 35 in, and then I move everything to the other side, so it becomes x to the power of 3x minus 35x is minus 34x. No, let me keep 105 on the right, and then I factor an x out. This becomes x squared minus 34 equals to 105. Okay, one way, for example, here is to say, oh, x multiplied by an integer is 105, so I got what I need, yes? Because I told you this is always good to have a constant number on the right, and I got it so easily. It's not wrong, it's correct, but unfortunately it will not give rise to a simpler solution, because how many factors of 105 are there, plus or minus? So x should be plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 7, and then I have plus or minus 15, and I have also plus or minus 35. I'm writing all integer factors of 105, and finally plus or minus 105. First of all, the numbers are a little bit bigger than those numbers, so checking them back into the original equation might be a little bit harder. But the number of terms that I have to check is not also reduced. So 1, 2, 3, 4, 5, 6, 7. There should be so if I remember correctly, so there should be another one, because 105 can be written as 5 times 21. 21 can also be written as 5 times 3 times 7. So 1, 3, 5, 7, and then 15. Oh, 21 is also there. I forgot to write plus or minus 21. So exactly, I have 16 cases to consider, but the numbers are bigger. But of course, it is not wrong. Okay, so you have to check them back, and then you see that only 7 will work in the original equation. Okay, I don't know, might be you can write it like this. You can write it as this one, and instead of 105, you can write 3 times 5 times 7. But considering different cases is a little bit hard. For example, if x is 7, you see that this will work here, because this one becomes exactly 15. Okay, but because here I have the product of 2 numbers, but here I have a product of 3 numbers, that is also the case that I have to consider a lot of cases. And keeping track of those cases might be even harder. But anyway, that is up to you which way you prefer to use. Okay. I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.